Hi, we're Group 18, and this is our senior project. I'm John Wallace.
I'm Devin Morrell.
And I'm Brandon Bayless, and we are the Wicked Wizard POV display.
We'll start with an overview of our system, then we'll show you a prototype demonstration, we'll go over the engineering requirements, and then we'll give you some recommendations for future seniors.
Alright, so back here we have our motor controller, which was pulled from a treadmill, and this is the transformer for said motor controller. Over here we have our power supply, which powers both the PCB and the BeagleBone. And the power coming from the power supply will actually run back here and up through these cables and through our slip ring, which will transfer the power from the non-rotating part of the system to the rotating part of the system. And this is our motor, also pulled from the treadmill. And connecting to this motor, we have several brackets to ensure that this is on here very stably. Obviously, we don't want anything swinging around at 1,000 RPM. And then, as we come closer here, we have several power converters in here. They're actually buck converters, and you can see there's 4 of them. And then we have our BeagleBone in here, which is really the brains of it. And then we'll now swing around to the PCB right here. You can see on the back side we have several LED drivers. And then right over here, very specifically, we have a couple magnets mounted to this bracket here. And those magnets hit what's right here. And on the back side you can see it right down here. And that's the Hall effect sensor that actually helps us measure the speed of the PCB while it's spinning around.
This is the Wicked Wizard POV display. Now the reason you see the lights blinking like this is because it's actually trying to display an animation. But the door is actually open here a little bit and the safety interlock is disengaged, so it actually won't spin no matter what. If we close the door, it'll engage the safety interlock and it'll start spinning at about 1,000 RPMs. So let's do that. And you should be able to see a globe spinning right there. You can see the continents moving from left to right. And the reason it looks a little bit choppy on camera is that the persistence of vision effect is actually a uniquely human trait. We see lights for about 1/25 of a second, and that causes the lights to sort of merge into a solid image. On the camera, however, it has a different frame rate and a different exposure time than your eyes, and that actually causes some jagged edges and some kind of tearing effects that you're probably seeing right now. So if I open the door, the safety interlock will disengage and it'll slow back down, and that'll allow you to change the video through the SD card, or if you need to, just turn the whole system off.
Alright, so here we have a little slideshow going on our Wicked Wizard POV display, and it's just going to cycle through these images. Here we have a topographical map of the Earth.
The following are our engineering requirements. The audible noise of the device must not be louder than 70 decibels at 5 feet. This would be similar to an average conversation. Next, the LED display must output at least 50 lux at 5 feet at full brightness. This would be equivalent to a dimly lit room. The device must also operate off of a standard wall outlet, which is 120 volts at 60 Hz.
The device must be able to continuously operate for 5 hours. This is our longevity test. Our refresh rate engineering requirement says the display must be able to display 30 frames per second at minimum. This is because most movies are displayed at 24 frames per second, so we want to make sure that we can get the full refresh rate so as you get a smooth picture. Our safety interlock engineering requirement says that if you open the door to the display will stop spinning in under 10 seconds. This is so that you are not injured by the display when you are changing the video. From standby, the system must be able to output full video in under 30 seconds. This is so when you want to watch a video, you don't have to wait too long for the video to start up. Our case strength engineering requirement says that during spontaneous deconstruction, no parts will exit the enclosure. This prevents users from getting injured if something goes wrong with the display. Vibrations created by the spinning system must not move the display more than 1 centimeter in any direction in 1 minute. This is so that it won't vibrate off any table you put it on. Our viewing angle engineering requirement says the display must be easily viewable from up to 30 degrees from normal. The only requirement that we didn't meet out of the 10 was the requirement for the longevity test. This required our display to run for 5 hours without incident. We failed this test because during the 5-hour test, after about 40 minutes, the SD card came detached from the spinning system and just started flying around inside the case, and we had to stop the test. Because of other technical problems before, we were not able to start this test until the day before the checkoff, or even less than the day before the checkoff, hours before the checkoff. And because of this, we weren't able to restart our test. And so we recommend that if you have any uber long tests, make sure you start them long before your checkoff and not within 12 hours of your checkoff. And make sure that if you have a spinning system, you understand the forces involved, and make sure to attach everything to your spinning system in a way that will keep it attached for up to 5 hours if that is your test requirement.
Senior design is a really long class, and you know, we've learned a lot, and we'd like to pass that on to you. When you're trying to debug your system, it's always easier to work with simple parts. So if you have small pieces that you can sort of make sure are working before you try to fix a problem with a much bigger system. A good example of this was when we were trying to debug our Hall effect sensor. The problem could have been in code, it could have been in hardware, it could have been anywhere. So we kind of decomposed it, and we made sure that the sensor was working by itself, just using an oscilloscope, and then we changed something in software and to determine if that was the cause. And breaking things into small pieces keeps things easier, especially when you've been up really late debugging. Circle K is about a 5-minute walk. We've done some testing, and it turns out that that is the best place to get a Polar Pop at 4 a.m.